All right, everyone. Welcome back to Legion School. So if you recall, we've been talking a lot about tasks and how they execute. Specifically, most recently, we've been talking about index-based tasks and how they are launched and how we execute them by breaking them down into slice tasks and then recursively breaking those slice tasks down into point tasks. What I want to do today is actually finish up our discussion of how slice and index-based tasks work. Specifically, what I want to look at is how they get moved around and how we do completion from remote nodes if we've actually moved slices to remote nodes. And I think that will probably not encompass the entire time. So then after that, what I want to do is just talk a little bit about the stealing mechanism that exists for moving both slice tasks and individual tasks around. And hopefully that will cover our entire time. And then at that point, I think we'll be done with most of our task stuff. And the next time we meet, we'll be able to start talking about the region tree stuff. So let's actually get started and let's actually dig in to some code. We'll do a little bit of a refresher just to remind ourselves where we've been starting. So I'm going to jump back to Legion tasks.cc here. Okay, and if you recall, we were looking at multitask trigger execution. And so what we did was we went through this whole function of multitask trigger execution, and we looked at all the different ways that we end up, all the different stages that we go through for executing index-based tasks. And if you recall, what we do is effectively continue slicing index-based tasks as much as the mapper wants, breaking them down into slices, which represent subsets of our index space, sending those slices to remote to whatever processor the mapper has assigned them to, either on the local node or remote node. We can recursively slice those slices into further subslices. And then eventually what we do is we end up triggering execution on those slices where we actually end up enumerating our points and mapping points and then launching those point tasks onto processors. And then once those point tasks are running, they operate just like any other single task, the same as if you had launched an individual task. And at that point, they operate, again, you're back running just like any other single task would run. So what I want to do today is actually talk about what happens as those point tasks begin finishing. So let's actually take a look at the point task, at what happens when a point task finishes executing. So let's see if I can find what I'm looking for here. So we have a point task class that has, that's used for it's effectively extends the single task interface. Has, some special virtual mapping or virtual methods for doing special things for the point task, but in general, it uses a lot of the underlying functionality of the single task class, just like the individual task does. Okay, so one of the first things that we get that's different about point tasks. You recall from when we looked at individual tasks are only considered complete once they have completed their operation, and all of their child operations that they've launched are also complete. This is also true for point tasks. And you recall that the method that we end up invoking when both of these conditions are true is trigger task complete. And that logic is all baked into the base task op class. So you don't need to worry about having it special for individual tasks or point tasks. It's all going to be the same. And what we have is this virtual task, trigger task complete, which we define specially for instances of the task op class. Just to refresh your memory of where that is, I'm going to just show you where that is. So if I look in legion tasks.h and I search for trigger task complete, you'll see that there's a pure virtual method on scrolling up here on the task op class. So trigger task complete and trigger task commit will both be invoked once all the operation itself has completed, as well as all of its child operations have completed. So let's jump back here. We're going to jump back to legiontask.cc and look at what happens when these point tasks actually get their trigger task complete call. So if we look for point task, trigger task complete. So here we are in the point task complete method. Now you recall that the individual task trigger task complete method, which we looked at a few sessions ago, does something a little different. Usually what it does is it actually tries to wrap up the operation, and if it's on a remote node, it sends back information to its owner node saying that it actually finished executing that operation. But in this case, the point task is not going to actually clean itself up. Instead, what it's going to do is actually notify its enclosing its parent slice task, what we call the slice owner for this point task, that it is actually finished operation, and it's going to be up to that slice task owner that enumerated this point task to actually do something else. Just to show you, I want to show you where this slice owner is declared, because it actually is a common. It's actually an important member variable for these different tasks. So if I jump to Legion tasks .h and I search for class point task, here you can see it actually extends the single task, which I'm telling you. And you'll see that really point tasks extend single tasks. They share all the same data structures, single task, plus 2 extra member data fields here. One is a pointer to the slice task owner that owns this point task, and the other is a point termination event, which we might look at a little later today. But this slice task owner gets filled in when the point gets enumerated. Effectively, when you create the point and you fill it in with all its member data, one of the things the slice task does is it actually sets the slice owner to point back to itself. And this gives the point task a reference back to its owner to know that the slice task that actually generated this point task. One important detail here is that you are always guaranteed that this pointer to the slice task will always be valid. Effectively, you can always dereference this. You're guaranteed that this point task will always be on the same node as the slice task that generated it. In the case where we actually move, let's say, like a locally mapped slice task to another node, which has a whole bunch of point tasks, what we do is we end up unpacking all the point tasks into their new slice task, and the pointer they reference will be a pointer to the slice task on the local node. So this will always be, this right here is a pointer that you can always dereference and do things with. Just to give you a contrary view of this, the slice tasks have a similar pointer that they track called the index owner, which tracks the index space owner. So let me actually show you where that is while we're here. Class slice task. So here's our slice task class. Again, you see it extends the multitask class, which is true of both slice tasks and index tasks. And I scroll down here past all the methods. And again, we have a whole bunch, we only have a few fields that are special for slice tasks. And one of them right here is this index owner pointer that we have. Now, one of the things that that's true, that's not necessarily true, that was true for the slice owner, that's not true here for this index owner, is that this pointer is not always valid. So even slice tasks that I mentioned the last time, that index tasks never ever leave the node on which they were created. Once we create one, it's just always going to be on the node where it was created. And then it's up to in order to send parts of that task remotely, you have to slice it up into pieces and then send the slices remotely. Well, when those slices go remotely, they keep this reference to this index owner pointer here. But this index pointer here, this index owner pointer that we have here, once we get moved remotely, is no longer a valid pointer for you to dereference. You don't know which pointer or where it might point in some other process that we unpack it in. But the reason that we keep it is so that we can, when we send messages back to our index owner, we know we can pass this index owner back, or we can serialize it in with a message and then pass it back to the node that actually has the index task. And then when we're unpacking that message, we can, unpack this pointer and know that it points back to the index task that we were initially pointing at on that creation node. So effectively, you can't always necessarily dereference this index owner task. You can only dereference it if you know that your slice is on the same node as the node that it was created on, where this index task actually resides. But in the case of the slice task, in the case of a point task where we actually have a slice owner, you can guarantee that you can actually always be, I actually want class point task here. In the case of a point task, you can always guarantee that the slice owner is on the same node as the point task, and therefore you can always dereference it. Okay, let's jump back here to Legion tasks .cc. Okay, and I'm going to go back to point task, trigger task execution. Trigger task complete is what I was looking for. Okay, so when we finish our task, our point task, what you'll notice is that we do a bunch of calls back to our slice owner to tell it that it has done different things. So for example, the first thing we do here is if we had any virtual map children, we couldn't actually consider ourselves mapped until all of our children are mapped. So once we've actually done this trigger task complete, we know that all of our children have mapped, and therefore we can tell the slice owner that our children have been mapped. If we created any privileges, if we created any new regions that we are then have privileges on with read-write access on those regions, we can pass those privileges back to our slice owner. So we can tell it that we've completed some privileges. And then what we do is we do this call to record child complete, which effectively tells the slice owner that we've actually we've actually completed our operation. So this point task can be considered complete. So let's actually look at what happens when that occurs. So if we go to slice task, record child complete. What you'll notice here is that this slice task is actually tracking a bunch of information about which points are not yet complete. Do you recall when we enumerated our points, we actually filled in this field saying how many enumerated points there were based on how many enumerated points there are. And then what we do is as the children complete, we decrement this counter. And as soon as we get, that all of our point tasks that we generated have completed, and we know that they've also, registered that they've completed all their child, or their children have and we've actually gotten our children complete invoked. Then we can actually trigger our children, we can actually trigger that all of our children, which in this case is all of our points, have actually been completed. So let's actually look at what that does. We search for trigger children, children complete. You'll notice that this is a method on a task op, which is the base class. And what that does is it says that we can actually, mark that we've completed all our children. And at this point, we can actually we'll be able to trigger our task complete for our slice task as long as we've actually gotten the complete call for this particular slice op. So I suppose this is an important detail, which is that even though the slice tasks don't actually, execute any application level code, they're still going through this pipeline. And so, what we're doing is we're using the proxy of having all of our point tasks execute as the proxy for all the children for these slice tasks. And the slice tasks are still going through the execution pipeline, but they're not actually doing any application code. So they still go through the runtime pipeline just like every other operation, but they don't need to actually run any application code. So by triggering children complete, we're marking that all of our point tasks have been complete. And then once we get our complete call, we'll be able to call this trigger task complete. So let's actually look at trigger task complete for a slice task. Okay, you see we get this trigger task complete call for a slice task. We turn around and call trigger slice complete, which is a member method on the slice task. We search for trigger slice complete. Okay, and you'll see that we do one of two things, depending on whether or not we are a remote slice or not. So if we're remote, what we're going to do is we're going to pack up the information about our slice task saying that we're complete, and we're going to send this information back to what we call the origin processor, the original processor that owns the index-based task associated with the slice task. In the case where we're not remote, we can actually dereference this index owner pointer that we were looking at before directly, because we know that we're on the same node as the index task that originally created us. So we know that this pointer is valid. Therefore, we can just immediately dereference that pointer and return all the information about this slice task. Let's actually look at this return slice complete call, because effectively what this message does is it packs up some necessary information, and then it sends that information back to the origin node, then unpacks it, and then it calls exactly the same return slice complete method. Okay, so let's look at return slice complete. Okay, and you'll notice that this is a method on an index-based task, so these are always on the node where we were owned. And one of the things that we do is we track how many points we have seen that have actually completed. So one of the arguments to this, you'll notice, is the number of points that this slice task is returning. So the index task knows the domain of the index space of points that we initially launched, it knows how many total points there are inside of that domain. And what we're looking for is to actually have seen that all of these points have actually come back and marked that they've been completed. So you see what we do is we have a little counter here in our index-based task that tracks the total number of completed points that we've observed. So we take a lock and we increment this count. Notice we might be getting multiple of these return slice completes from different slices coming back all at the same time, possibly from remote nodes or local nodes or so forth. So we have to take this lock. We update this count of how many complete points there are. And then what we can do is we can check to see whether or not we've actually seen the whole set of all the points that we were supposed to generate for this index-based task launch. And if we have, what we can do is we can then mark this this trigger children complete again. You can think again as this index-based task is again just like slice task is going through the pipeline. It's not actually running any application code, but it's going through all the stages of the pipeline just like any other task. And it's considered that all of its children are complete once all of its slices that it launched off have come back to it saying that we've enumerated all of the points, or we've run all of the different point tasks for our particular task, and we've gotten notifications that they've all been complete. So once that's happened, we know that all of our children are complete, and therefore we can call trigger children complete. That actually goes back to that same base call in task op, which then once we've actually gotten our complete call, we'll call trigger task for index tasks. So let's actually look at that. Let's actually look at index task, if I can capitalize properly. Trigger task complete. Okay, and what you see here is that this index-based task, we get this trigger task complete call only once all of our point tasks for actually executing this particular index-based task have been completed. And then we get that transitively from all of their slice tasks having been reported that they're complete as well. And once we get this, we can actually, do all the things that we can do that an individual task also did, such as returning privileges back to our parent context. So in some cases, if we created regions or so forth, we have new privileges, rewrite privileges on regions, so we get to return those back to our owner task. Remember that index tasks never leave the node where they're actually created. So we know that referencing our pointer, our parent context is always the context in which we were created. We have a special case here for reductions. In the case where we actually have a reduction future, we actually set that value here. Otherwise, if we have a future map that represents the futures for all of our different points, we mark that they're all complete now. And then once we've done that, we can mark that we've actually completed this operation. And that marks that we've actually finished executing all of the different point tasks inside of our index-based task. Okay, so that's how the process of once we've effectively, you can think of it as there's a big fan. The way that we think of index-based tasks is there's a big fan out of all of our tasks. We're constantly breaking index tasks into slice tasks, and then slices into other slices, and then slices into point tasks. And so we do this big fan out to get this index-based task running across as many processors as the mapper requests. And then once they're done, we're effectively collapsing all of the state back to this one index-based task on the origin node where we actually initiate operations, so that we can tell any other operations which depend on this index-based task that we've actually finished running this whole collection of points. We finished running tasks for each of the different points inside of this index-based task launch. One important detail that I think I mentioned briefly at the end of the last talk that I want to re-emphasize here, just to point it out to you. Let's go back to slice task trigger task execution, or sorry, I guess it's a trigger task complete. And I guess what we really want is trigger slice complete. So one of the important details here of these slice tasks and how we enumerate them is that you'll notice that one way to think about this is we have effectively a tree of tasks that we're launching off to execute an index-based task. At the root, we have a big index-based task. At the next level, we have as many slice tasks as the mapper asked us to generate in the first generation. And then each preceding generation, we have as many slices that the mapper asked for. And really, it's only the slices at the leaves of this tree that actually end up enumerating points and executing anything. And so one of the things that we want to avoid is when we actually have to pass information back to the root of this tree of the index task owner task at the root of this tree. We don't actually want to have to jump back through all the intermediate slices that we generated as part of the mapping process. And so what we do is we actually can send. This is the reason that we track this index owner pointer as we create new slices. So if we actually look at pack remote complete, let's actually look at that. Look at slice task, pack remote complete. What you see here, this method is not too complicated. We pack up a little bit of information about the state of our region trees, but we pack up some privilege information. We pack up some of our reduction information. But one of the important things that we do, the first thing that we notice that we serialize here is this index owner pointer, which I mentioned is possibly not local to the node that you're on. And what this index owner node allows us to do is that it actually allows the slice tasks at the leaves of this big slice task tree that we've generated for launching this index space. It allows them to send their information directly back to the index task owner at the root of this tree without needing to propagate it back through all the intermediate slices that we generated as part of the mapping process. And so, what this means is that you can actually fan out index spaces recursively to a big set of nodes in the machine. But then when we go to actually collapse and actually clean up all of our stuff, once we know that all of our point tasks have completed, we can actually send information directly back to that index owner without having to bounce it all around the machine through all the nodes that it came through. And so this is really, an optimization that we're doing. And it makes, it significantly reduces the amount of communication we have to do to actually move information back to our index owner. So it's just something to be aware of when you are thinking about how these slice tasks actually execute and clean themselves up. So they're actually passing information directly back to their index task owner. Okay. So one other detail you may have noticed as we've been going through this process, it's actually is that we looked at how the completion mechanism works for slice tasks, but there's actually two other parallel operations which happen in a very similar manner. Let's actually look at I think I went point task perform mapping is what I'm actually looking for. Yes, this is what I'm looking for. You'll also notice that there are two other parallel operations which occur, sort of propagating the state information from point tasks back to slice tasks and back to index-based tasks, and they're exactly what you would expect. So the first one is this mapping process. So we want to know when a point task has actually completed mapping. We want to propagate that information back to our slice owner to mark that the point task has finished mapping. So for example, we're in point task perform mapping. You recall that this call is map all regions, which does all the actual heavy lifting. If we succeeded, the first thing that our point task does is it actually calls record child mapped. So if we actually look at slice task record child map, notice that this is right above record child complete, which we saw before for registering that a point task had actually completed. So we have the exact same process for recording the children are mapped. And then once we know that all of our points have been mapped inside of this point task or inside of the slice task, we can call trigger slice mapped. Effectively, we can count ourselves as mapped once we know that all of our point tasks have mapped. And then that goes through the exact same process that we went through with record child complete in order to notify the index task owner when all of the point tasks inside of this index task have actually finished mapping. So it's the exact same parallel process. You'll notice that there's sort of a symmetry between all of these mapper calls. They all have the same sort of flavors, just with different variations for the operation being performed. And I mentioned there were three of them. So there's one for handling when all of our point tasks have mapped. There's one for handling when all of our point tasks are complete. And there's one here for handling when all of our point tasks have committed. And so this does all of the stuff that you would expect it to do. They're all effectively isomorphic to each other, just for different phases of the pipeline for the execution of this index-based task. Okay. Let's see. Does anyone have any questions about how this completion works, or how distribution of slice tasks and point tasks all work? We've gone over it, in about a session and a half now, which I think is actually pretty fast. Is anyone confused or lost in any way before I move on to talking about stealing and stuff for the second half of this lecture? Okay, I'm going to take the silence as a no, that everyone is on board and not lost in any way. Okay, so what I want to do now is actually transition just a little bit. Effectively now, one of the things that we have available to us is we know now how both individual tasks and slice tasks can get moved around the machine to actually be able to be run on other nodes. And once we have that, it makes it much easier to understand how the stealing mechanism works inside of the process managers that we looked at a few lessons ago. Effectively, now we understand how these different what the different task operations are that can be in this queue or in the set of available tasks ready for stealing. And at that point, what we can do is we can understand, when they get moved around, we know how things actually complete, because we've seen the processes for what happens when individual tasks and slice tasks get executed remotely. So let's actually jump back here to process to legion tasks.cc. Actually, I guess what I really want to go to is runtime.cc, so we can actually look at where the request. We'll start at where the request first comes into the mapper to actually ask it to perform, to ask it if it wants to do any stealing. So let's see if I can remember the name of this mapper call. Vote mapper target. Here we go. Target task steal. Okay. Here's the call to invoke the mapper to ask it if it would like to perform any stealing. And let me give you some context. This is a part of the code we've actually looked at before. So we are here inside of Processor Manager, inside of Perform Mapping Operations, which you recall is what we call whenever we don't have enough outstanding tasks. This is effectively the scheduler call that comes into to our Processor Manager saying, this processor doesn't have enough outstanding tasks for some context. Why don't you go ahead and try and map some tasks onto this processor, or do something else with them in order to actually get some more outstanding computation going on this processor. And so you notice that we're iterating over, just to refresh your memory, we're iterating over the sets of queues, which have for each of the different mappers, saying which tasks they have, which are ready to execute. And these queues are recording. If you recall, each of these queues are recording are the operations which are ready to map, but which have not yet been mapped. So this ready queues, which is really just a vector of doubly ended queues. So we index into it by our mapper ID. We keep a separate queue for each of the different mappers for tracking which operations and specifically which tasks are unmapped in this particular case, but are ready to be mapped. And of course, now we've been through the task execution, so we know that this ready queue, while it holds generic task ops, we know that it actually only holds two kinds of task ops. Actually, it's only allowed to hold individual tasks and slice tasks, because effectively those are the two things that dictate the granularity at which stealing and scheduling can actually occur. Effectively, what can happen is, individual tasks obviously can be moved around the machine by the mapper and can be stolen. But the mapper is also dictating the size of the granularity of execution for index-based tasks by breaking them into slices. So slices are the granularity at which things can be stolen and things are moved around inside of the machine. So we know that this ready queue now only holds individual tasks and slice tasks. Okay, so you recall that what we do is we make a copy of all the pointers to all these tasks which are potentially ready to be mapped. And we do, our normal call to figure out which task to schedule. But of course, we also do this other step here where we actually ask the mapper if it would like to possibly find tasks which are ready for, or possibly invoke a steal request on another remote processor. And what we do here is we actually call this invoke mapper target task steal mapper call, which goes ahead and actually processes up a bunch of, it allows the mapper to fill in this optional steal request data structure. I think we actually requested this, you see that this is actually a multi-map of processors to mapper IDs. So effectively what you're saying here is the sets of processors and a set of mapper IDs for each one of those processors for which we might want to, for which mappers have requested steals. So we're filling in this data structure, this steal targets data structure. One of the important things we do is we pass in a blacklist, which is reference to, which is a copy of the processors which this mapper has already requested outstanding steal requests. Effectively, what we want to do here with this blacklist is avoid mappers sending lots and lots and lots of steal requests to processors which we know don't have any work. So this blacklist is initially empty, but as soon as you do an initial attempted steal to one of these processors, what we're going to end up doing is adding that processor to a blacklist until one of two things happens. Either one is we actually do a successful steal, in which case when that information comes back, we can remove that processor from the blacklist. Otherwise, if we don't do a successful steal, that processor remains on the blacklist until that processor sends us an advertisement saying that it has additional work to do, which is available for stealing. And we're going to see how all of this works. So after we do our steal request, we do is we take this special lock here, which we use for protecting the stealing data structures. You'll see that we get a reference to our current blacklist. Notice that because we reference the stealing lock here twice. We do so once in read-only mode just to make a copy of this blacklist to pass into the mapper call. But then we have a second, when we retake the lock, we get a new reference to it because this actual blacklist may have changed since the last time that we saw it. And then once that happens, what we do is we actually prune out any of the processors the mapper requested, which are actually on the blacklist for this particular mapper. And what we do is we look at the steal targets that the mapper requested, and if they're not on the blacklist and they actually exist and they're not our local processor, we add them to our list of possible steal targets. And then we add them also to the blacklist in order to make sure that we don't try to steal from them again until we either have a successful steal or we've gotten notification that we actually have additional work to do. Okay, so let's actually see what happens. What we do is we effectively build up the stealing targets data structure, and then we do is we send all of the steal requests in bulk for all of the different mappers. So down here at the bottom of this call, there's actually a call down here for right here. Finally, if we had any steal targets, so not stealing targets empty, we send our steal requests. Let's actually see how that works. I search for send steal requests. This is actually there are two versions. There's the message manager for actually packaging it up, but the important one is actually this runtime one. So what we do is you see we iterate over this multi-map of processors and mapper IDs. And for each of these different processors, we're going to send a message with all of the mapper IDs that have requested from that processor. What you do is we serialize up our target processor, we serialize up ourselves, this current, what we call the thief, the manager, or the processor which is doing the stealing request. We count up however many mappers there are that have requested steals from this processor. We serialize all of these mappers into our data structure, and then we send this steal request. So if we look at send steal request, I guess I already had it highlighted. This comes back to our message managers. We package it up with a steal message request. We look at steal message. We see that when we this is the handling code for the message manager. Once that message comes in on the remote processor, we go to runtime arrow handle steal. What you do is we unpack all of the information. So we unpack our target processor. We unpack the thief, the processor which we're stealing from, which is requesting the steals. We count how many members there were. We unpack those. And then we call this process steal request on the processor manager, which is the target of the steal requests. So we search for process manager, processor manager, process steal request. And what you see happens here is we actually are going to end up invoking the mapper to actually see whether or not we want to allow any steal operations from the queue that this particular mapper is managing. This is one of the important distinctions about how Legion does stealing, which is different than a lot of other systems, which is we don't make stealing happen implicitly. Effectively, the mappers are in total control of the stealing process. So it's up to them to decide which of the individual tasks and slice tasks that are available inside of the queue that this mapper is managing to decide which ones they want to steal. So what we see here is we're iterating over all the mapper IDs that we have steal requests for on this particular processor. So we get the mapper IDs. One of the things we do is we iterate over the ready queues and we pull out the ones that are available for stealing. So you see what we do is we have a check here to see which tasks are available to be stolen. So you recall that there's this is stealable call, which we're invoking on either the point tasks or the slice tasks. And this is stealable is controlled by the mapper. It's controlled for individual tasks by setting the spawn task field on the task object. Let me actually show you remind you where this comes from, just so you can make the connection. So we jump back to legion.h, and we actually look at class task in here. You recall that there's this, let's see if I can find it here, spawn task. And this gets set, is supposed to be set as part of the select task options mapper call. So if I look at select task options, one of the things that you're supposed to set is this spawn task field. And effectively what it does, it has similar semantics to something like Silk, where effectively you say if you want this task spawned, this effectively enables the individual task for stealing. So you can control stealing for individual tasks like this. Alternatively, for slice tasks, whether or not the slice is available for stealing or not is controlled by the domain split the data structure that you get in slice domain. So if I search for slice domain, here's our slice domain call. You remember we built up a vector of these domain split objects for each one of our slices. And just to show you where this is, domain slice is up here inside of this mapper object. And you'll notice that this last field is the stealable field, saying whether or not this slice task is stealable or not. So the mapper is under control over deciding which of the individual tasks and which of the slice tasks are stealable. So at this point, we can jump back to runtime.cc. And we can come back to processor manager, process steal request. Okay, so we're back here. We were pruning out the sets of tasks that were available to be stolen. So that's where this is stealable call comes in. It's been completely controlled by the mapper. And then there's also this other case here, which is we're not allowed to steal locally mapped tasks. And there's a very obvious reason for this, which is locally mapped tasks are always mapped on the processor where they were originally created, which means that once they're effectively coming into this queue, we've already mapped them, and we already know exactly which processor we want to launch them to both map and run them on. And so, even if the mapper has made a mistake and marked that these tasks can be stealable, we don't actually want them to be stolen, because if we try to run these tasks which have been mapped to a particular processor on some other processor, bad things tend to happen. And so effectively, this is just protecting the mapper from itself and making sure that it's not doing something dumb that's going to break the correctness of our code. Okay, so once what we've done here is build up a little data structure, this vector of mapper tasks, which has information about all the tasks which are eligible for stealing for this particular mapper as part of this the steal request that this mapper is handling from another mapper on a different processor. Okay, so this is not empty. What we do is we actually invoke the mapper, ask it whether or not it wants to enable any of these tasks to be stolen. We give it a list of the tasks which it has available to steal, and then we ask it to fill in, a set of tasks which it's going to allow to be stolen from it. And so, of course, notice that because we built a little temporary data structure here for these mapper tasks, again, just like when we're scheduling of tasks, once we retake our lock, we actually have to go through and see which ones are still actually available to be stolen. It's possible that while we were performing this mapper call, another utility processor came along, it ran the scheduler for the same processor and the same mapper, and the mapper actually decided to actually map some tasks that it may not have known it was going to allow for stealing, at which point those tasks have now been launched off onto this processor or sent to some other processor or something, and so they're no longer valid for stealing. And so what this loop right here is doing is it's going through and checking to see effectively which of our tasks are still available to be stolen, that the mapper has actually allowed to be stolen. And then what we can do is we can actually, once this is has actually, we've found all of our tasks that are ready to be stolen, we pull them all off of our ready queue here. So we can mark that we found them. If we found them, we can move them onto the ones that we've actually stolen. And then what we can do is we can actually, we do a little bit of bookkeeping here to make sure we keep track of whether or not we still have any stolen tasks or not. And then once we're done with pulling all of these tasks that the mapper has asked to allow to be stolen off of the queue, we can actually send information back to the task or to the processor which actually requested the steal. We can send these task operations back. So here's our case. If we actually have stolen tasks, we can actually send them back. You'll notice here there's a special call here, prepare steal, which actually asks the task to make sure that they're ready to be stolen. And it used to be that this prepare steal call would effectively do the pre-mapping stage of the task. In fact, that's what they do now. We actually have cleaned this up a little bit. It used to be that it was possible for this pre-mapping phase to fail if we weren't going to allow the task to be stolen, if the pre-mapping fail was unsuccessful. The reason for this is that pre-mapping used to involve performing a whole bunch of close operations, which involved closing the region tree on the local node before we could actually move the task remotely. But now we've actually fixed that, and that's no longer the case. So it's almost universally true that this prepare steal will always return true, saying that it's safe to steal these tasks. Of course, tasks can actually be stolen multiple times. So we can actually, in the case where a task had already been either sent remotely or already stolen, we knew that this task will actually return true very quickly because we know that we've already gone through the overhead of stealing before. Okay, and so what happens here is if we successfully steal this task, what we can do is we can record that we've successfully stolen it. And then what we do is we pack up all these tasks and send them back to the processor that actually requested them. Actually, it looks like I need to come back and look at this code. It looks like some stuff might not have been. Or yeah, I guess here it is. Send tasks. We send all of the stolen tasks back to the processor that actually requested the steal. Now, one of the important things that actually happens here, you'll notice this is very subtle, is that in the case where we were unable to actually successfully steal a task from this particular mapper, we record that we failed to perform the steal operation. And the reason for this is that what we want to do is actually remember the combination of the mapper ID and processor that tried to do this steal, so the mapper ID on the stealing processor, actually asked us for the steal request and it didn't work. And what that means is we know that processor, that mapper for that processor, has us on its blacklist now as a list of processors on which they cannot steal from, because they know that there's effectively no work here that's currently ready to be executed. However, what we're going to do is we're going to keep track of that until we actually get some new work, which we know is possibly available for stealing, at which point we're going to send an advertisement back to the processor that had a failed steal request, which will allow it to remove itself from its blacklist. So you'll notice here that we have this failed thief's data structure, which is just storing a pair of mapper ID and processor, saying that this is a set of we record that there was a failed steal request here. And the place where you see that this gets used is actually inside of perform mapping operations. So this is, remember again, this is our scheduler call that we invoke pretty regularly. And what you'll see is down here at the bottom, what you'll notice is that we'll notice that if stealing is not disabled, and we've actually recorded that we have mappers with work. You remember this mappers with work gets filled in if we still have available tasks which are eligible for stealing on this local processor. Then we know that we have work which is available potentially for stealing. And so what we do is we actually send advertisements for any of our mappers with work. We issue advertisements to any of the processors which have tried to steal from us in the past, but which were unsuccessful, in which case we know that they have us on our blacklist. So if we look at this issue advertisements call, it's actually right down here. You'll notice that we, again, take our thief lock and we iterate through all of our thieves. We look for ones in which we have a mapper ID corresponding to the ones that we know to mappers that have work, and then we can actually send back. Where we do is we send advertisements back to those processors saying, "Hey, we actually have work for you that might be eligible for stealing again." In which case, they can actually remove us from our blacklist and therefore be eligible for sending steal requests back to this processor again. So you notice that if we just look at this send advertisements call, I can spell. Right, all we're doing is we're packaging up a bunch of processors and saying which ones, for which processors and which mappers we have this work that is available for stealing. We send these advertisements back to the failed thieves, and then once they get these process advertisement messages, if I actually look at processor manager, see if I can get it. Let's see if it's a process advertisement. Here we go. So here's an advertisement that comes back from those calls, and what you see is we take we take our stealing lock and we can remove from the blacklist the advertiser saying that he might actually have worked, so he no longer needs to be on the blacklist. And of course, one of the important things that we do is we actually enable the scheduler whenever this happens. And the reason for that is that we actually want to allow the mapper to possibly issue a steal request once this happens, even if it doesn't necessarily have any work to do. Okay, so you'll notice that steal request is really under control of the mappers. They can control which individual tasks and which slice tasks inside this queue get moved around. Importantly, stealing, the current interface allows both push and pull models for moving tasks around. So mappers can effectively request the tasks either get pushed to remote nodes by changing the target processor, or pulled by changing by actually doing things like sending. They can do things like actually moving tasks around multiple times, so you can push tasks around through these queues many times before you actually decide to map it. And the same thing for stealing. You can keep tasks on the queue as long as you want to, and able to allow stealing requests to come in and actually take that work from you. It's a little bit of a trade-off to decide how long to keep things on those ready queues before actually mapping them. And again, we leave these kinds of decisions up to the mapper so that they can do a good job for whatever particular application they want to move around. The important detail from the perspective of tasks is just that the only tasks that you'll find on those ready queues are index-based tasks, slice tasks and individual tasks. And you guys now all know what those are, and you know how they get moved around. And I guess hopefully that will give you a complete picture of how these task objects get moved around inside the machine as part of the execution of Legion applications. Okay, so I think at the end of today, unless anyone has any questions or has anything else that they want to cover, I think we've covered most of the detail about how tasks and operations and the Legion pipeline actually works. And I think the next time we're actually going to be ready to start talking about the region tree data structures, which is really where most of the magic in Legion really occurs. So if anyone has any questions, I'll be happy to take them now. But if not, I think we're done for today. Okay, no questions? All right, everyone, take some time and prepare yourself this weekend for starting the region tree next week. We'll see you guys. I guess on Monday, Sean will probably be talking about the low level, but I'll be back next Wednesday to talk about the high level region tree data structures.